Welcome to Chapter 7. In this lecture, we're going to discuss log linear and log-log models and multiple linear regression analysis. So a log-log and a log-linear estimate either marginal effects as percent change, that's log-log, or log-linear, or an elasticity, which is a log-log model. The models are estimated taking natural logs of the dependent variable, the independent variable, or both. The first model we're going to discuss is a log linear model. The second one is a log-log model. And I understand the difference between LOG and LN. Every time we say LOG, we actually mean LN, natural log. I know it's annoying and frustrating, but this is the case in some things in economics that we kind of take great liberty at what these things mean. So I know that log is log base 10, but we always just call it log. I don't know why. Here's a graph of y versus x. We can see that there's a non-linear relationship. This is y, this is x, this is non-linear. Whereas if I take the natural log of y and graph it against x, it is now linear. Therefore, I've turned something non-linear that's exponential, thus the natural log, so something that's exponential, and turned it to something linear. This is the intuition behind what we're trying to do with log linear or log-log models, is take a nonlinear thing and make it linear. The log linear model, basically what this means is you take the natural log of your y variable, but then the linear aspect is your independent variable. It remains the same. And in general, the log y will not be given to you. You actually have to create it in Excel. It's really easy. Equal sign ln, and then open sign paren, put in wherever your y lives, close paren, and then just copy down. It's not hard to take the natural log in Excel or any other program. And so this is what we're doing. Now, beta 1 has a different interpretation if we do a log linear model. In this case is on average, if x1 increases by 1 unit, y will increase or decrease depending on this sign by, you take this value, beta 1, and you multiply it by 100%. So it turns it into a percentage change. This is only an approximation because this is a nonlinear function. We're like trying to linearize something that's nonlinear. There is a way to make it a little bit more accurate. I used to go into it. I don't anymore. You can Google it or look it up. But in general, this is what everybody does when they report their research. Okay, the intuition behind this log linear model is that I think the best way to understand it is if we're going to estimate the relationship between salary versus years of education, it's probably unreasonable to assume that if you get an additional year of education, that the increase in salary is going to be constant. That's what a linear model would say. But we could see a place or assume that if we get an additional year of education, the percent change in our salary is the same. So for lower levels of income, then the value of the salary will change by less, but the percentage between lower and higher values of salary should remain the same. This is what we're assuming with the log linear model, is that the value of salary is not constant, but the percentage change in salary for an additional year of education, we could think of this as constant. Here's an example of a log linear model. In this case, the dependent variable is the natural log of energy per capita, and then this is GDP per capita, and it's actually in thousands. And so the slope is interpreted as on average. If GDP per capita increases by 1,000, we're increasing it by 1,000 because this is what GDP per capita is in. Then the energy consumption per capita goes up by, you take this coefficient estimate, you multiply it by 100, and then you put a percent by it. So you just move the decimal place 2 points. So we get 2.6%. So on average, if GDP per capita goes up by $1,000, then energy consumption per capita goes up by 2%, 2.6%, and then we can see this is statistically significant. So again, you take your coefficient estimate, you multiply it by 100, move the decimal place 2 places to the right, and put a percent by it. Now let's look for if for dummy variables, how we would interpret this. And so the omitted category is apparently South America. So what does this European coefficient mean? It means that on average, if a country is in Europe, its energy consumption per capita is 50.47% higher relative to South America. And then to look at North America, we can see that on average, energy consumption per capita is 57% higher in North America relative to the omitted category, which is South America. And Europe is not statistically significant. North America is statistically significant at the 10% level, or we call marginally statistically significant. Now, instead of doing a log linear model, we can do log-log. So we take the log of the y, or the dependent variable, and the log of the x variable as well. So this is why it's log-log. Beta 1 is interpreted as, on average, if x1 increases by 1%, then y increases by beta 1%. So in this case, unlike the log linear model, you take this number and put a percent behind it. And then, so you don't multiply it by 100 if you do log-log. So in this case, the log-log model, this beta 1 is an elasticity. So an empirical example of this log-log model is that if GDP per capita goes up by 1%, then the per capita increase in energy goes up by 0.69%. So again, for log-log models, you do not move the decimal place, whereas in log linear we do. When do you use log linear models and log models? Usually if your dependent variable is a dollar amount, then we typically use log linear models. But if some of the dollar values are 0, then you can't use this log linear model because log 0 is undefined. So you'll have some undefined. So that's the exception to the rule. But in general, if your y variables are in dollars, taking logs are a lot of the time what we do. Another thing you can do is look at scatter plots. And then really my recommendation is to pay attention to what others have done for similar applications, and monkey see, monkey do what they do. If other people do this, then you should probably do so too, or have a good reason that you're not doing it. That's for the log linear model. For the log-log model, my opinion is that it's pretty much never a great choice, because basically you can see here that we're saying that the elasticity, beta 1's an elasticity, is constant for all values of x. That is usually a very, very constraining assumption and not typically consistent with what's happening with data. And so my personal opinion is that the log-log model is not the way to go, but you know, other people like it. That's why we're discussing it. So it's up to you. Okay, I hope this helped you guys.